Okay, so we're going to hit highlights of sections 1.1 to 1.5. Again, this is supposed to be mostly review. I'm going to start off by talking a little bit in section 1.1 about interval notation and set builder notation and graph notation for intervals. That's going to be something we're going to use all throughout the course. Okay, so let's do this. So we're going to talk a little bit about intervals. Can you guys all see the screen okay? All right. So we're going to talk a little bit about intervals right now. And what I mean by an interval is on a number line, we've got, we can represent intervals. So for example, you guys are probably used to in previous classes, if I create an interval here, we'll do several examples here. I'm going to draw a bunch of number lines here. Okay. Then we're going to draw some intervals on these number lines. And I'm going to show you how we notate or write intervals in this class. Okay. So the first thing is we could have like an A and a B on the number line. Those are just going to be some random numbers that they could be like -5 and 8, but we're just going to leave them as A and B for now. And what we're going to do is we're going to create an interval. You're used to in the past using open holes and closed holes probably. Like in the past, you might do something like do a closed hole and a closed hole and draw a line. And that represents the interval from A to B, which means this is the set of all numbers between A and B, including A and B, because I did the solid dots. If I did an open dot, for example, that would mean I'm including A, but not including B, because the open hole means you don't include the endpoint. You guys should be probably have used that in the past, okay? But in this class, we're going to use a different notation than the open dot and the closed dot. We're going to use a bracket and a parenthesis, okay? So I'm going to put this in right after intervals here. A bracket is the same thing as the closed hole, and a parenthesis is the same thing as the open hole that you used before, okay? So for example, if I do a parenthesis and a parenthesis from A to B and do this, this is all the numbers between A and B, okay? Not including A and not including B, because it's like an open hole. So that's how we write this. This is called number line notation. I'll write that down here. This is called number line notation, where you actually just draw this whole is going to be number line notation. I can write this in something called interval notation as well. It's a different notation. It's just a different way of expressing the same interval. Interval just means set of numbers in an interval. So like all the numbers between 0 and 1, or all the numbers between -8 and 5. Okay. So an interval notation, the way I'd write this is the picture actually corresponds to the notation. So the way I write it is I put the parenthesis because I have a parenthesis here. And then I do the A, comma, the B. And then I do the other parenthesis. So this matches this. And this matches that. And then I just do the A and B in the order they appear. That looks like an ordered pair from when we graph, but it's in this context, it's different than that, okay? It's expressing an interval in this context. Okay, now I could do an interval, another one from A to B, where this is called a half open interval, where maybe I'm going to include one side and not include the other. So I got the bracket on the left, which means I'm including A, because remember the bracket's like the solid hole. And then the parenthesis on the right means I'm not including B. So this is all the numbers between A and B, including A, but not including B. So like, for example, if this were 3 and I'm going to erase this in a second, but if this were 3 and 4, these two numbers, this would be all the numbers between 3 and 4, like 3.5, 3 3/4, 3.78936, 3.95, 3.01, 794. Just every number, there's an infinite amount of numbers in there, aren't there? Because we're not just dealing with whole numbers here. We're looking at any possible decimal even that could be in between there. So it's an infinite amount of numbers. The way I'd write that is exactly an interval notation. I put the bracket because the bracket corresponds to this bracket. And then I do A, B, and then I put the parenthesis because the parenthesis corresponds to that. Okay. I could also do, I can have it closed on both sides. So I could have parenthesis here, or bracket, whoops, and bracket, and a line. That means I include both endpoints. So the way I write that is A to B in interval notation. Now I can have infinite intervals too. Okay. I can also have infinite intervals. So I can have like an interval that starts at A and just goes on forever to the right. So it's like 3 to infinity. Okay, remember there's on the ends of the number line to the right is infinity and to the left is negative infinity. Okay. So the way I write this one is I put a parenthesis for A on the left, and then I'm going to go all the way to infinity. But infinity is not a number, guys. It's a concept. It just means keep going. So whenever I have an infinity, I always put a parenthesis with it. I can't put a bracket on infinity because it's not an actual number I can include. It's just a concept that says keep going to the right. Okay, I could also have something like this, where maybe I include B and then I go to negative infinity. Remember, this is the negative infinity side of the number line. This is the infinity side of the number line. Okay, so the way I'm going to express that is I start at the left. Well, on the left side is negative infinity in this interval, right? So I've got to start with negative infinity, and I'm going to end on the right at B. I'm going to put a bracket there to correspond to that bracket. And then I'm going to put a parenthesis here because I can't include negative infinity because it's not a number, it's just a concept. All right. And then the last one I could have is I could just have something that goes both ways, covers the entire real number line. Well, that's just the whole real number line is just negative infinity to infinity. That's everything. That's every single number. That's the infinite interval in both directions. So this is the notation we use. This is interval notation right here. This is number line notation. We're going to use both of those. The last one, which is a bit harder, is called set builder. And that uses inequality symbols. Okay. So I'm going to make these a different color so the eye draws them a little bit. Okay. So that's set builder. So interval and number line. So what does set builder look like? Well, set builder is this really funky notation where we use something called a brace. A brace is like a squiggly parenthesis. You can see it on your keyboard above the bracket symbol. So set builder says the set of all x's such that, and this you just got to memorize this. This could be any letter I want. You could use X, Y, Z, doesn't matter what letter. And then we're going to express a rule right here, a rule. And that rule is going to tell us how to define the interval we're looking at, okay? And that rule is going to use mathematical symbols, and it's going to use inequality symbols. So I want to get all the numbers between A and B. So the way I do that is I say A is less than X is less than B, and I'm going to explain why that makes sense, logical sense. Because this basically says that X is greater than A if you see the greater than symbol is facing the X. And it says, and X is less than B. So this is all the X's or arbitrary numbers or any number X that is bigger than A and less than B. Well, isn't a number in here? So pick a number in here. Isn't that a number that's bigger than A and less than B? Sure is. So that's how I write it. So in general, the format of set builder, okay, the format of this part, this rule part, is just going to be something less than x less than, well, let's write that better. It's going to be something less than x less than something else. And it's going to be two less than symbols. And that basically says that x is sandwiched between whatever this is and whatever that is. The number x that is, and this means that any x or any number that I could put in for x that satisfies this will be in this interval. Okay. Now we can actually change whether it's a less than or equal depending upon whether I have a bracket or a parenthesis. The reason I used a less than, a strict less than in this one is because we don't want to include B and we don't want to include A because these are parentheses. So whenever I see a parenthesis, okay, this is important. I'm going to erase this now. When we're in this set builder notation, okay, a parenthesis is going to correspond for set builder. A parenthesis is going to correspond to a less than symbol, and a bracket is going to correspond to a less than or equal to symbol, because bracket means we're going to include that, which means it could be less than or equal to that endpoint. Okay, so this one's a good example. This next one's a great example of that. Okay, so in this next one, I'm going to do the same thing. Set of all x such that, and of course, I'm going to have my A and my B again as my right and left. I'm going to stick a less than x less than symbol there. But because this is a bracket over here, that means the left one is going to be a less than or equal because I'm allowed to include A. All right, then this next one is going to be set of all x such that A is less than x is less than B, but I'm going to include both of them so they both become less than or equals because they're both brackets. And then I do the same thing with infinity. Infinity is the same pattern. So I do x and I do A is less than x is less than infinity. So I'm following this pattern, right? Notice A, infinity. And then since they're both parentheses, they're both less thans instead of less than or equals. And this one, same pattern, follow the same pattern. I do the negative infinity, less than x, less than b, and it's a less than or equal here because that's a bracket. And then for the last one, negative infinity is less than x is less than infinity. Those are both less thans because I can't include infinity because it's not a number. Remember, anytime you have an infinity, you always use a parenthesis. So this is how we express different types of intervals. We call this an open interval. Open means that it's parentheses on both sides. We call this half open because there's a parenthesis on one side. When we call this one closed. Closed refers to brackets. You could also call this one half closed because it does have a closed on one end. All right. So that's some basics of interval notation. All right, let's do some examples of that just to get some practice. So if I write -3 to 8, and then here's another one. Set of all x such that 2 is less than or equal to x is less than infinity. Okay, take a second, and I want you to write this first one into set builder. Set builder's notation kind of like that, okay, like that one. And I want you to write this one in interval notation. Go ahead and do that and write your answers, if you can, in the chat. So the first one, if I were to write it in set builder, I do my little X with the line. That means the set of all X's, possible X's, such that -3, it's a less than or equal to X less than 8. And the reason it's a less than or equal is because this corresponds, the bracket means it's a less than or equal, and the parenthesis makes it a less than. Okay. And then the second one, I agree with what you guys wrote. This just looks like it goes from 2 to infinity. And the reason I have the bracket again is it's a less than or equal. And then of course with infinity, we always have a parenthesis. All right. So that's how we do set builder. And interval and number line notation. Let's hit up a little bit of review now of order of operations. All right, so the order of operations, if you guys remember, is first we do anything in parentheses. And then we do anything, any exponents. We evaluate any exponents. And then we do multiplication or division from left to right. And then we do addition or subtraction, whichever comes first, from left to right. Some of you guys have memorized PEMDAS. Please excuse my dear Aunt Sally. I don't actually like PEMDAS, and I'm going to explain why I don't like PEMDAS. The reason I don't like PEMDAS is because it makes it look like you should do multiplication before division, doesn't it? And it makes it look like you should do addition before subtraction, but that is not the case. The multiplication and division are grouped, as are the addition and subtraction. You do multiplication or division, whatever comes first from left to right. So it's possible you would do a division first if it comes first from left to right before multiplication. So if you had something like 8 divided by 2 times 3, okay, you're actually going to do the division first. If you do the division first, you get 4 times 3, because 8 divided by 2 is 4, and then you get 12. But if you did the other way around, you'd get a different answer than 12, okay? You'd get 8 divided by 6 if you do the multiplication first, which is definitely not 12. So I don't really care for PEMDAS that much. I don't think it's a great tool. I think as long as you can remember that the M and the D and the A and the S are grouped, it's okay. But if you don't remember that, you get a lot of problems wrong. So if I take an example here, (10 squared minus 100 divided by 5 squared times 2 minus 3. Why don't you guys take a second to do that and report your answer? Let's do this. Let's do, there's no parentheses. Let's hit the exponents first. 10 squared is 100. 5 squared is 25. And now it looks like I'll do multiplication or division from left to right. So the first division I come to from left to right, the first thing multiplication division I come to from left to right is this division right here. So I'll do that. 100 divided by 25 is 4. Now let's go do the multiplication. Now I subtract 92 minus 3, which is in fact 89, which is what I was seeing as the most common answer. All right. So that's kind of a highlight there on order of operations. Okay, let's do some linear equations. If we hit some linear equations here. So the basic principles of linear equations are I can add, subtract, multiply, or divide the same thing to both sides of an equation as a strategy for solving it and getting x by itself. The only thing I can't divide both sides of the equation by is 0. But other than that rule, I can add, subtract, multiply, or divide both sides of the equation by the same thing. So just a very basic equation. If I have 3x minus 7 equals negative 21, I want to get that x alone, so I'm going to add 7 to both sides. Negative 21 plus 7 is negative 14. Then I'm going to divide both sides by 3 to get that x alone. And I end up with x equals minus 14 thirds, okay? But I could get much more complex than that. I'm going to erase that. As much of a pain it is to do that. And we can hit some more complex examples. So for example, I could do something of the nature 5x minus 2x minus 2 is equal to x plus 3 times x minus 11. So now I've just basically complexified the problem a little bit by just adding parentheses and adding extra steps to the problem. So what I need to do is just simplify both sides of the equation to make it a lot more manageable. So what I do first is I notice that since I've got a minus in front of this parenthetical expression here, I need to apply that minus to both terms inside. So what that basically means is that it changes the signs of both things inside. So this is a positive 2x inside. It'll now become a negative 2x. You can almost think about this as like multiplying negative 1 times both, distributing negative 1 through to both terms. And then a negative of a negative 2 is going to be a positive 2. So when you have a negative in front of a set of parentheses, it just changes the signs of both things inside. And then over here, I'm going to do just some distributing. I'm going to distribute the 3 to both of those terms. And I would get x plus 3x minus 33, because I'm taking 3, the minus carries through, and 3 times 11 is 33. Okay, now I'm going to combine like terms. Okay, so for example, these are like terms on that side, and these are like terms on that side. So that gets me 3x plus 2 is equal to 4x minus 33. Okay. Now, this is a problem where I have two appearances of x, one on one side, one on the other. Well, I only want to have one appearance of x because I want to get x by itself. So a really quick way to get one appearance of x is just to subtract off, like for example, I could subtract off 3x from both sides. That's legal because we can add and subtract the same thing from both sides. And what that does is it eliminates the 3x on the left side. And then these combine as like terms to give me 1x. So now I'm left with 2 equals 4x minus 3x is 1x, or just x, minus 33. Now to get the x alone, it's pretty easy because I have a minus 33. So I just add a positive 33 to both sides. These cancel, and I'm left with x equaling 35. That's my final answer because now I have x alone. So now I'm going to make up another one. Give that one a try. Give that one a try and report your answer. All right, let's do this. Distributing the 7, I would get 7x minus 21 plus the 4x. Distributing the 2, I get 2x minus 22. Now here I'm distributing like a minus 2. You can think of that subtraction symbol as almost like distributing a minus 2. So that'd be minus 4, then minus 2 times minus 5x is a plus 10x. All right, now combining like terms, the 7x and the 4x give me an 11x minus 21. Here I combine the 2x and the 10x, and then the negative 22 and the negative 4. So the 2x and the 10x is a 12x. And then minus 26. Now I'll subtract 11x off to get rid of one of the appearances of x. I could subtract the 12x off too, it doesn't matter, you get the same answer. So that gets me negative 21 is equaling 12x minus 11x is x minus 26. I now add 26 to both sides to balance out the minus 26 there. These are gone, and I do get 5 equaling x. Okay. Now let's do one with fractions and talk about the idea of clearing fractions. Clearing the fractions. Okay, this is a technique we're going to use throughout the entire class for various types of problems. So if I take a very simple problem, let's just take as simple a one as I can make up that has all fractions in it. X over 5 minus 1 over 2 is equal to x over 6. Okay. So in that one, hang on a minute here. In that one, this has fractions in it. I don't want any fractions in that, guys. But I can't just like erase the fraction. So I have to do some sort of mathematical trick to eliminate the fraction. So what I do is I notice for 5, 2, and 6, those three numbers have a least common multiple of 30. That's the least common multiple of those denominators. So what I'm going to do is I'm literally going to multiply both sides of the equation by 30 and watch what happens. So I'm going to take 30 times this first term minus 30 times the second term is equal to 30 times the x over 6. That's completely legal because I can multiply the left and the right-hand side by the same thing. So I multiply each term on each side by the same thing. That's the same as multiplying the whole left and the whole right. So the reason why I'm multiplying each of those by 30 is because now some cross canceling occurs. When I take 30 and multiply by a fraction, I can actually cancel the 5 with the 30 and get a 6 up there because 30 over 5 is 6. 30 over 2 is 15 and 30 over 6 is 5. So what I just did is using a legal algebra rule, I cleared those fractions out. So now I'm left with 6 times x, 6x, minus 15 times 1 is 15, is equal to 5x. Now I could subtract the 6x for both sides. I'm left with negative 15 is equal to 5x minus 6x, which is negative x. To change that to a positive x, I divide both sides by negative 1. And then it makes those a positive. And I'm left with 15 equaling x, or x equaling 15. So that's a procedure called clearing the fraction. So what I do is I find the least common multiple of the three denominators, and I multiply every term in the equation by that least common multiple. Let's do a little bit more complex one. Okay. So I've got that one now. So similar, the least common multiple for 4, 6, and 3 should be 12. That's the lowest multiple they have in common. That would be the common denominator if I got a common denominator. So what I'm going to do is I'm going to take 12 times each of these terms. So the x plus 1 over 4. I'm going to do 12 times the 1/6 plus the 12 times the 2 minus x over 3. I'm going to put these numerators in parentheses just so I know I need to distribute, okay? So now if I look, the 12 over 4 is a 3, the 12 over 6 is a 2, and the 12 over 3 is a 4. Now, okay, I have to do just some distributing. I got to distribute that 3 to both of those. You got to distribute the 4 to both of those. So this will be 3x plus 3 when I distribute the 3 is equal to 2 times 1, which is 2, plus 4 times 2 is 8. And then it's a minus 4 times x, which is a minus 4x. Combining a couple like terms here that can combine the 2 and the 8 on the right. I'm going to add 4x to both sides to get rid of that appearance of x. So that gets me 7x plus 3 is equaling 10. Now I'll take this 3 away here. And I get a 7x equaling 7, dividing both sides by 7. I get x equals 1 in the end. Okay, let's try this one. Give that one a shot and see if you can, if you guys can all get this. All right, let's do this. So looks like the least common multiple for those denominators, which would be the common denominator, is 21. So what I'm going to do is I'm going to multiply every one of these terms, these fractions. I got to multiply the 5 by 21 too, guys. If you didn't do that, you may have made an error. Minus 21 times the x plus 2 over 7. So you got to multiply the whole number terms in addition to both the fraction terms by that number as well. I'm going to put parentheses around these so I know that I'm distributing and I'm done. So 21 over 3 is going to be a 7, and 21 over 7 is going to be a 3. So now I'm going to do some distributing here. The 7 I'm going to distribute to those two. And then it's going to actually be a minus 3 that I'm distributing to those two because I got the minus in front. So this ends up becoming 7x plus 7 when I distribute. 21 times 5 is 105. And then it's a minus 3 times x and a minus 3 times positive 2, which is a minus 6. So now I got 7x plus 7. I can combine the 105 and the minus 6 to get 99 minus 3x. I'm going to go ahead and add a 3x to both sides here. That's going to give me a 10x plus 7 equals 99. Subtracting the 7 from both sides. I get a 10x equaling 92, dividing both sides by 10. I do get x equals 92 over 10, which is 46 over 5 if I reduce it. If I cut the top and bottom in half. All right, so that hits all the highlights I had planned to hit in 1.1 to 1.5. 1.5 has some word problem stuff that's pretty basic. That's review as well. I'm not going to spend a lot of time on that. I'll just answer questions as they come in on my math lab. But that hits the big highlights in chapter 1.